So we're going to continue with our discussion of Java fork join pool, focusing now on something called the common fork join pool. And we're going to begin our discussion with motivating why there is a common fork join pool and what benefits it provides. And the main thing it provides is it is designed to help maximize processor core utilization, to try to get the processor cores used as effectively as possible. So there's this thing that's called the common fork join pool. It's a static method called common pool that's used as a factory method to obtain the common fork join pool. There's only one of them, so it's kind of a singleton at the same time. And it's available and is appropriate for most programs' needs. There can only be one of these things. That's intentional. There are only so many cores, and the intention of the common fork join pool is to provide a single point of access to all those cores. This pool is used by any fork join task that's not submitted to a specified pool within a process. So by default, you'll use this one unless you go to the trouble of making yourself your own pool. This is a great picture of a common pool, obviously from days before COVID, but this is a good example of trying to put everything into one pool. The reason to put everything into one pool, or at least the reason to have the option of putting everything into one pool, is to optimize resource utilization, since this one and only pool can be aware of which cores are used globally within a process. And the goal is to maximize processor core utilization by work stealing. If you watch the videos from last week, you'll see a discussion about what work stealing is. And work stealing is a really cool mechanism that's provided with the Java fork join pool, and it basically is used to try to keep all the cores running. And so this is taking the work stealing concept, which works on individual pools as well, and trying to centralize everything into just a single pool. This concept of global versus local resource management and the benefits and trade-offs therein is very common in computing. Think, for example, about the Java Heap, the free store, where dynamic memory is allocated from. There's intentionally a global heap so that all threads within a process will use that global heap, rather than partitioning things up into little chunks, making it harder to have global optimization of memory. This is basically the same idea, just applied to computation as opposed to applied to memory. And there's other domains as well. Sometimes organizations like to centralize things like, say, HR or legal or accounting and so on in different parts of the business. They try to have some common services that are infrastructurally related. The common fork join pool has another purpose, which we aren't going to talk a heck of a lot about in this course, but we'll talk about in my sibling course to this one, which will be going in the fall. And this is called the Java Parallel Streams Framework. And the common fork join pool is used in the Java Parallel Streams Framework in order to provide a common context to run computations in all the parallel streams within a process. It's also used, or can be used optionally, in the Java Completable Futures Framework, which we also will not spend time on in this class, but which is an interesting way of doing things that have a very asynchronous flavor to them. So that, again, is a topic that you might want to learn about if you take the class next fall, my class next fall. By default, the common fork join pool has one less thread than the number of cores that are available to the underlying execution environment or the virtual machine. And if you take a look at the implementation of the make common pool method, this is something that's used inside of the implementation of the Java fork join pool. Make common pool will set the parallelism of the common fork join pool to be the number of processor cores, that's what the available processors method provides, minus one. So if we had a 4-core processor, then the number of threads in the pool would be set to 3. And you might ask, that's kind of weird, why is that? And I'll talk about why in a second. Here's how you can find out what the parallelism level is in the common fork join pool. If you say fork join pool dot get common pool parallelism, it'll return to you the number of threads that are part of the common fork join pool. The reason why it's always one less than the number of cores is because the invoking thread, that is whatever thread is going to be calling the method to invoke the common fork join pool, will also be included in the pool. So it basically borrows the invoking thread and uses that. And therefore, a program that uses the common fork join pool can leverage all the processor cores if that's what you desire. And we'll talk later about ways to limit or expand the number of threads that are part of the common fork join pool. But by default, you get one less the number of cores as the number of threads, and then the invoking thread itself can also be used in that way as well. Now, the issue that we have to confront here is that the default number of threads in the fork join pool may be inadequate in some circumstances. So here's a good example. If we have, let's say for sake of argument, we have 4 cores, but we want to do some operations that are going to be larger than the number of cores. And in particular, if the operations we're going to do are going to be blocking operations. So if we have blocking operations, that means, say, downloading a bunch of images as part of an image processing task or an image processing app, then in that case, you're going to have some problems using only the default number of cores. Why is that, you might ask? Well, the problem here is that when you're doing operations that block, like downloading images, then when a thread is blocked in the pool and there's only a fixed number of threads and the number of threads is less than the number of operations you're trying to do, then even though there's other computations that could be done, you've chewed up a thread or all the threads that are available to do those computations. So the way that blocking operations work, which is why I/O-bound tasks should be treated differently from computation-bound tasks or CPU-bound tasks, is because while a thread is blocked in I/O, there really is other things that could be going on. And therefore, you don't want to have a situation where you're blocked on all the threads when in fact there could be other things that could be running if only you had more threads. So it turns out that one of the key things that will happen in this case is underutilizing the number of cores. So we're going to talk about ways to fix that problem. So therefore, it's often desirable, not always desirable, but often desirable, especially for I/O-bound tasks, to be able to expand or contract the common fork join pool size programmatically. And we'll see there's a couple different ways to do it. One way to do this is by modifying a system property. So there's a system property called java.util.concurrent.forkjoinpool.common.parallelism. There's a property with that name. And you can set that property to whatever you want it to be. So you could set it to, say, 10. And irrespective of the number of cores on your processor, you'd end up with 10 threads. The problem there is it's often hard to know what the default value should be. And another problem here is that modifying this property affects all the common fork join pool usage within a process, because it's making that be the number of things, which might otherwise be too big or too small in a Goldilocks-like sense. Yet another problem with doing things by the system property is that this property can only be changed or set before the common fork join pool is initialized. And it's initialized, the common fork join pool is initialized on demand the first time it's actually used. So setting this value is a little bit tricky. You have to know just exactly where to do it, and that can be confusing. So therefore, we need something beyond setting this static value in order to be able to increase the fork join pool size. And we'd like to be able to do this automatically based on runtime properties, not things you have to know about ahead of time. So how do we do that? Well, we're going to be using something called the managed blocker. And managed blocker is essentially a mechanism which you will have to know how to use for your programming assignment number 4A. And this gives you the ability, or this gives the fork join pool, the common fork join pool, the ability to expand and contract automatically. Excuse me. And what it does is it temporarily adds worker threads to the common fork join pool as needed. And this ability to do so, this ability to add these threads on demand automatically as needed, is particularly useful when tasks wait on I/O, synchronizers, or blocking queues. So there's certain circumstances where threads might block for various reasons, either because they're blocked on I/O, or they're blocked on synchronizers like a reentrant lock or a semaphore, or they're blocked on blocking queues, which under the hood use reentrant locks and condition objects that you've learned from earlier lessons. And in those cases, the ability to add more threads to the common fork join pool comes in handy. Now, something to remember about managed blocker, it can only be used with the common fork join pool. It can't be used with anything else, it can't be used with any other thread pool in general, and it can't be used with any other instance of fork join pool in particular. It can only be used with the common fork join pool. And another thing to note, and we'll go into this in more detail here shortly, it's very helpful to encapsulate the managed blocker mechanism within some kind of wrapper, because the underlying mechanism is a little bit goofy and complicated, and therefore you're better off if you encapsulate it. And I'll show you one neat way to encapsulate it. So what the fork join pool does, or common fork join pool does, is it reclaims threads during periods of non-use and then makes it possible to reinstate them on later use as they're needed. So that's the end of the overview of how to use the common fork join pool to maximize processor core utilization. And we'll go into more detail about all these mechanisms here shortly.